Hello everyone. In the lecture today, we will continue the topic in soil properties. In our previous lecture, we introduced the soil classification and the presence of clay, and now we will go through the mechanical properties of the soils. As in geotechnical engineering, there are some typical soil mechanical properties, such as strength parameters including cohesion C and friction angle phi, compressibility and consolidation. Also, the soils has elastic properties such as modulus of elasticity, capital E, and new Poisson's ratio. For pavement design, we need to think about what properties are generally required. In general, for pavement design, we have to consider their resilient modulus. This one is quite similar to elastic modulus, but it's measured at a different way. The second one is Poisson's ratio. Also, we have to consider the deformation properties under high number of the repeated loading, which we are trying to reproduce the traffic on the road. Also, obviously, we have to take into account about the effect of waters, the environmental impact such as the temperatures, freezing soil effect, and so on. To make it more specific, we categorize the soil properties needed for the pavement design in three types: stiffness, California bearing ratio, and permanent deformation resistance. Here we will focus on stiffness. For stiffness, it's actually measured by three variables: coefficient of reaction, which is usually applied for subgrade layers, Poisson's ratio, and the resilience modulus, MR. MR could be modeled with some linear functions or nonlinear functions. First, let's go to check the definition of modulus of reaction for subgrade. Here we will consider the slab. The figure here shows the reaction on the slab under the pressure. P is the pressure applied to the slab, and delta is the displacement. We can identify the relationship between the pressure and the displacement in the equation here, P equal to K times delta. Here the little k is just defined as the modulus of the subgrade reaction. Based on the units of the pressure and the displacement, we define the unit of the modulus of reaction as kilopascal per meter. For the slab, we can see that the reactive pressure only depends on the deflection at a point, and it's not related to any neighboring point. We cannot observe any shear interactions along the slab. In the real world, generally the plate load test is applied to determine the modulus of reaction for subgrade and subbase layers in pavement. Usually the ASHTO test 22278 is conducted. The figure on the left demonstrates the configuration of the plate load test. It has a 30-inch diameter plate stacked with some stacked plates, hydraulic jack, and a reflection frame. Usually, this kind of test is conducted in field at the field moisture, and it's installed at a fixed location to do some static test. During the test, the load applied to the plate increased at every 10 psi, and then we measure the deflection for the plate. With the test data, we can draw the relationship between the pressure and the plate deflection. In the real test, usually we will get a curve about this relationship, but from our previous page, we defined that there's a linear relationship between the pressure and the plate displacement. The slope of this line would be the modulus of reaction. So with the real data, we will try to find out a line to fit to the actual curve and then measure the slope. This will just be the value of the modulus of reaction. The two figures here shows the devices that are applied for the plate load test. The modulus of subgrade reaction is actually not a material property. The value measured from the plate load test actually varies with the size of the loading plate. The figure here shows the relationship between K values and the diameters of the loading plate. With larger diameter of the plate, the K values will be smaller. But in general, we define that the K value at 30 inches of diameter will be the modulus of reaction for subgrade. In addition, we can find that modulus of subgrade reaction is highly related to elastic modulus, capital E. The equation here actually shows the how we find out the theoretical relationship between K and capital E. Here, P over delta is just the modulus of reaction. And if we say that the Poisson's ratio nu is 0.5, then we can identify K as capital E over 1.18 times A. Here A is defined as the radius of the plate. You can see that in these equations, both E and nu are material properties. They are not related to the size of the plate, but the modulus of reaction is highly related to the value of the radius for the plate. The second mechanical property, which might be the most important one for pavement design, is the resilient modulus. This one measures the elastic modulus of the subgrade of granular-based sub-base material under repeated loading. It's usually measured with the resilient modulus test. The figure on the left here actually shows the result from the test. It finds out the relationship between the stress and strain. During the test, an axial load will be applied to the test materials repeatedly, and we know that as the number of the repetition increases, the plastic strain of the material due to each load repetition will decrease. And eventually, after 100 to 200 repetitions, the strain can be totally recovered. Where you will observe a cycle about the relationship between stress and strain. And with this cycle, you can identify the value of resilient modulus. In this figure, you can find out that based on the corners of the cycle, you can identify the recoverable strain epsilon d and the deviator stress sigma d. With these two variables, you can determine resilient modulus as sigma d over epsilon d. In general, we will use the ASHTO test 307 to conduct the resilient modulus test, and the figure on the right actually shows the device we applied for the test. In the resilient modulus test, an axial load is applied to the test materials periodically, and is actually assigned to the materials under a given confining stress, which is S3 or is a sigma 3 as what we show in previous page. The load will start from a very small value and then increase gradually to its peak and then drop back to the smaller value. During the test, we will also observe the deformation of the test material, and then we can identify the relationship between the stress and deformation to determine the modulus of resilience. Now let's see how we can read the data from the test and how to estimate the resilient modulus with the test data. The figure here actually shows the test result of the sample material with the fixed confining stress. So sigma 3 here is 10 psi. You will actually observe 3 cycles in this figure. Actually, each one represents the result from 1 repetition. Now let's take the third cycle on the right as an example. In order to identify the resilient modulus, you need to specify the deviator stress, which will be sigma d, and the recoverable strain, that will be epsilon d, and the resilient modulus is sigma d over epsilon d. In the MR test, we actually conduct a lot of sequences, and each sequence will have one unique confining stress and axial stress. From the test, we can get the value of the deviator stress, which will be cyclic stress here. It's equivalent to sigma d, and also resilient strain epsilon d, and we also estimate the value of the resilient modulus. And now with multiple sequences, we can find out the set of values of sigma d, epsilon d, and MR. And then we can find out the relationship between the resilience modulus with respect to the axial loading and confining loading. Now we need to think about how to present test result appropriately. First, we have to consider the definition of two new terms, box stress and the deviator stress. They actually comes from the triaxial test. For this test, we will apply both axial stress and confining stress to a cylinder. So here, sigma 1 is axial stress, and sigma 3 is a confining stress. And then we can say that the box stress is theta equal to sigma 1 plus 2 sigma 3. We also define the mean stress as P equal to theta over 3. And the deviator stress is defined as Q equal to sigma 1 minus sigma 3. Now for the results from the previous example, we can first find out the relationship between the resilient modulus and the box stress. The figure actually shows the result under different confining stress, 3 psi, 5, 10, 15, and 20. You can find that all the points are actually aligned to a line, which means we can find a line to fit all the data points. With the statistical analysis, we find that the resilient modulus MR will equal to 16.3 times theta to the power of 0.55. Here all the units will be kilopascal. If we consider the relationship between the resilience modulus to the deviator stress, we find that the deviator stress is also an important factor. So we can do another fit about the relationship between MR and theta and sigma d. So we find MR equal to 6.19 times theta to the power of 0.74 times sigma d to the power of minus 0.078. Also, the units of all the variables are kilopascal. For MR, it's megapascal. From the empirical data, we actually find that the resilient modulus is a function of a lot of variables, including the box stress, the pressure applied to the material, shear stress, density of the material, and the moisture contents. Generally, when you increase the box stress and the density of the material, the stiffness of the material can be increased. If you increase the shear stress or the moisture contents, the material will be softer. We can further summarize the factors affecting the resilient modulus. First, increasing box stress will significantly increase the value of resilient modulus, while increasing shear stress will cause a significant reduction of MR. In addition, broader grading of the material will result in higher MR values, but the increase is not that significant. With more fines in the material, the MR values will be smaller. If we have more larger size particles or higher density for the material, then the MR values will be larger. Finally, increasing the moisture content will result in dramatic reduction of the MR values. There are a lot of regression models to describe the relationship between the resilience modulus and the stresses. The first one that I want to introduce is the K-theta model. Here, MR is in the function of theta, and the PA here represents 1 kilopascal. The second one is Uzan model. The resilience modulus is in the function of theta and sigma d, the deviator stress. And last one is the ASHTO model. Here, MR is in the function of theta and tau oct. Here, tau oct is the octahedral stress, and it's defined as square root of 2 times sigma d over 3. For all these models, Ki represent the coefficients which are calibrated from the real data, and the coefficients actually varies with the water content, fine content, type of the soil, and so on. These two figures show the effect of water contents on the resilience modulus. The one on the left shows the result from granule B material, and the one on the right is from granule A material. Basically, granule B material has more fine particles than granule A. You can see that the 3 lines in granule B material are forced apart to each other, while in granule A, it's more concentrated. With this comparison, we can say that the resilience modulus is more sensitive to water contents when the percentage of the fine particles is higher. For different types of soils, the value of resilience modulus will be very different. And for each soil group, there's a typical values of MR. The table here shows the range and typical values of MR for each soil group defined by ASHTO method. For the example of A5 group, you can find that the MR ranges from 117 to 176 megapascal, and the typical value is 138. And you can also find out the typical values of the resilience modulus for the soil groups identified by the USCS method. So that will be all about the lecture today. Thank you very much for your attention.